All right. The objective for today is to know three forms of radioactive decay. These are the primary types of radiation that you hear about and you'll be studying about, and be able to show the results of two of them. As you're taking notes, you want to make sure that you're using abbreviations in there, because if you try to write down every word, you're going to be missing pieces and parts. So for note purposes, try to abbreviate when you can. Send your texting friends this information and put the words in text speak. It goes much faster. We're going to start off with the three types of radiation, give you a little background about them, what they are, how they behave. And then we're going to talk about how they break apart, how they decay, and why they decay. Nuclear decay is a release of millions of times more energy per atom than an ordinary chemical reaction. When we're talking about nuclear decay, we're talking about the nucleus of the atom. In the nucleus of the atom, when it breaks apart, it releases a huge amount of energy. In an ordinary chemical reaction, we're talking about what the electrons in the atom are doing. The electrons control chemical reactions, and they produce much less energy in their reactions than do the nucleus, where the protons and neutrons are stored. When they break apart and rearrange, they release a tremendous amount of energy. This is that energy that we find on the sun. Nuclear power plants utilizes this, nuclear reactors, energy engines, nuclear bombs. Huge amount of energy released when we rearrange those nuclei. The spontaneous breaking apart of the nucleons inside the nucleus. And it does this, the atom tries to become stable. When the nucleus is not stable, it starts kicking things out of the nucleus, protons and neutrons, until it becomes stable. That's the whole premise behind nuclear decay. It naturally happens. It goes at its own pace. Some things decay in fractions of a second. Other things take billions and billions of years. It just depends on what isotope we're talking about, a specific type of atom. There are three basic types of radiation. The first type is gamma rays. Gamma rays are abbreviated with the Greek letter gamma. That's that little Y-looking thing at the end of gamma rays. That's kind of a curly Q on the front of the Y, Greek letter gamma. In science, we abbreviate most things. Borrow different languages, whether it's Latin, Greek, whatever it may be, to utilize our abbreviations. Second type of nuclear decay is called alpha particles, abbreviated with the Greek letter alpha. If you were to put a dot on the left-hand side of the alpha with a little line coming in from it, kind of looks like a fish. Greek letter alpha. And then finally, beta particles, the third type of radiation, abbreviated with the Greek letter beta. Beta is usually tilted to the right. However, when you put it into print, it has to use its space so it doesn't interfere with the next letter coming up. So they stack it straight up and down here. But if somebody's handwriting it, you'll see it tilted forward. It has that little tail on the front end of the B. Gamma, alpha, and beta particles. Is that a question over here? If you look at these images up here, we have paper, aluminum, and lead to show the penetrating ability of each of the types of radiation. Gamma rays are the most penetrating. They go through paper, they go through aluminum, they'll go through up to 4 or 5 inches of lead. I think 6 inches of lead is the sweet spot for stopping the gamma rays, but a significant chunk of lead is dense enough and thick enough in order to stop the gamma rays. For example, gamma rays right now are going through your bodies, going in one side, coming out the other, and they're not even touching any of the atoms that make you up. Because they are so very, very, very small, they're able to wave their way in between the spaces or in the empty space of your atoms, not even touching the material of the atoms. They're just going through that empty space that makes you up and coming right out the other side. Beta particles are the size of electrons, and they're oftentimes described as an electron because they're about the same thing as an electron. They're able to penetrate paper, but a couple centimeters of aluminum will stop them. They can't go through that. And the last one is referred to as the kind of Mack truck of radiation. It's the biggest radioactive particle. It's called the alpha particle. It's the size of a helium nucleus, and it's stopped by just a simple sheet of paper. Your clothing would stop this particle, wouldn't be able to get through. Your skin easily stops it. It's not very penetrating at all. However, if you get hit with enough of any of these, they will do damage. That's what radiation relies on, overwhelming you with many, many, many of one of those or a combination of them. That's where the problems come in. Questions before we move on with the characteristics? For alpha decay, you imagine the nucleus on the left-hand side being made up of protons and neutrons. Doesn't matter which is which. We'll say the protons are blue, the neutrons are white. If you have a radioactive nucleus, it's not stable. Sometimes it kicks out an alpha particle trying to become stable. When it does, it loses 4 units of mass. So when we abbreviate it, we put a 4 in superscript, indicating it has 4 mass units that have been removed. 2 of those mass units are protons. And when you look at the periodic table, element number 2 in the periodic table is helium. So that 2 tells you the element, connects it to the symbol He. The 4 tells you the mass of that isotope. And an isotope is just a specific atom. When we know the exact mass of the atom, we call it an isotope. Beta decay involves a beta particle. It's a fast-moving electron. This fast-moving electron gets shot out of the nucleus of the atom. Remember, nuclear radiation, nuclear decay all originates in that nucleus of the atom. That's where the materials are coming from, where the radiation is shooting out of. So if you imagine again the nucleus being made up of protons and neutrons, blue protons, white neutrons, a red electron comes flying out of the nucleus of the atom. That happens when a neutron changes to a proton. When a neutron changes to a proton in the nucleus of the atom, again, the nucleus is trying to become stable, so it tries this, it changes. When it does, there's a little itty bitty bit of material still left over, and that little bit of material is formed into an electron. So that neutron regroups, rearranges, changes into a proton and an electron. The electron comes flying out of the nucleus, while the proton stays in the nucleus. It changes the element it was, trying to make itself more stable. particle is abbreviated with a Greek letter beta. It has a superscripted 0 because the mass is about 2,000 times smaller than a neutron or a proton. Since it's so small, we estimate its mass to be 0, so put a 0 there. It has no mass, even though it has a little bit. It's just really, really small. And because an electron is the opposite of a proton in charge, protons are positive, electrons are negative, we put a -1 on there to indicate its negative nature, its electron, opposite of a proton. That's how we abbreviate it. Sometimes you'll see it with the letter E instead of the letter beta, probably because the computer didn't have the key for beta on there, so E was easier to find. E standing for electron. Still have the superscript 0, the subscript -1. Those are the key characteristics of the particles. The mass on top, the number of protons on the bottom. Since it's the opposite of a proton, we put a -1 to show opposite. We'll be using those particles now in decay sequences. When we talk about radiation, remember there are 3 types still. Gamma ray emission is just pure energy coming out of the nucleus of the atom. It is given off during these decay reactions, and it happens most of the time. There's always energy coming out of a radioactive decay. So consequently, we just kind of ignore it because it doesn't help us in naming or figuring out the age of rocks. It helps when we're talking about energy and conservation of energy and whether we're going to use that energy to do something else. But when we're looking at just radioactive decay to find the age of things, it doesn't really help. So we pretty much just ignore the gamma rays. Realizing they're there, but we're not really doing anything with them. Alpha decay is a more important piece. An alpha particle, again, has 4 mass units. 2 protons, 2 neutrons. Each of them have a mass of 1. So if you count them, 4, that's their mass. 2 of them are protons, and that's the symbol there for an alpha particle. Superscripted 4, subscript 2, symbol He. Oftentimes, you'll see the alpha there instead of He. They're interchangeable. Just like the E is interchangeable with beta. See them both ways. The numbers, however, will always be the same. 4 on top, 2 on bottom. All right, let's go ahead and apply this in a decay example. Thorium-230 is your example for the first one. Thorium-230. 230 is the isotope number. The isotope number, again, is a specific mass of an atom. When we know the specific mass of an atom, we call it an isotope. Go ahead and find thorium now, if you would, on your periodic tables. When you find it, call out the number it is, so everybody else can find it quickly. If you would, so everybody else can find it. 90 is thorium. 90 is how all the elements are arranged in the periodic table. It's called the atomic number. The atomic number is in order 1 to 118. 90 is thorium's position in the periodic table. 90 is also the number of protons that each and every thorium have. You will notice below thorium, in that little box, you have something that's a weird number, 232.0381. That's an average mass of all the thoriums that are out there. It's not the mass of a specific one. 230 is the mass of this specific one here. And it happens to match pretty closely the average mass. All right, now if you would, put the lines on there in front of the 2 arrows. You have a subscript line, a superscript line for the 2 numbers. And then you have a baseline for the symbol. This is what we do anytime we have a reaction in chemistry. We start with the reactants on the left. We put the arrows on here to produce the products on the right. In this case, it's a nuclear reaction, so we call the reactants on the left-hand side the parents. These are the parent isotopes. And on the right-hand side, they produce the daughter isotopes. So parents and daughters. That's what we talk about with radioactive decay. All right, now you found thorium. What's the symbol for thorium, Evan? The symbol for thorium. TH. Capital T, lowercase h. Every time you write the symbol for an element, it's been abbreviated this way for over 250 years. Don't change the symbol. Put what it's supposed to be. That's its name. That's what it goes by. Capital T, lowercase h. Now the next piece on here is the number of protons. Let's see, Madison. How many protons does thorium have? What's its number? 90. So we put that on the subscripted line, the lower one. 90 protons. Once you know thorium, you know 90. If you know 90, then you know thorium. They connect. The last piece on here is the mass of this isotope specifically. Parker, what's the mass of this isotope specifically on here? It's on the screen, not on your table. 230 is its mass. That tells you the mass of the isotope. It's also the name of the isotope. It's how we name it based on what mass it has. 90 of those units are protons. That means 140 of them are neutrons. All right. Thorium-230 undergoes alpha decay. That's this upper arrow right here. If an alpha particle is kicked out of the thorium, what's left behind? Well, let's go ahead and look first at the mass. If an alpha particle leaves, will it be heavier, lighter, or the same mass as it was before, Sam? Lighter. What will its lightness number now be? How much mass, Janelle, will it have if it loses an alpha particle? How much does an alpha particle weigh? What's the mass of the alpha particle? I'm pointing to it on the screen. Can you see? Let's see. Go back to your notes. How about this one? Can you see it any easier? There you go. The mass is the one on the top I'm pointing to with my cursor. I'm pointing it on the screen. I can't tell if you can see the cursor on there. The big number is the mass. What's the mass? 4. So that's what you should have in your notes, because that's going to be an important number to remember. If you didn't write that down, you need to have that. Because in the future, when I ask, what's the mass of an alpha particle, Janelle, you'll say 4. So if 4 units leave, we're just walking this through now. When 4 units leave, and it was 230, what will it now be? It was 230. 4 units have left because an alpha particle left. What's still remaining? I'm still working with you. Yes, this is a question I originally asked you in the beginning. We're trying to get to the same answer. There you go. That's all you do. Subtract 4 from the mass because it has 4 mass units that are kicked out of the nucleus. Now 4 lighter. Questions about that piece? All right. Of those units, how many of them were protons, Shelby? It has 88 left. Good. Because 2 protons left when that alpha particle was kicked out. 4 total particles, 2 of them were protons. If it has 88 protons in there, Jonah, what is it now? Say again? Radium. Good. Ra is the symbol. And that's what we put on the line to show the radioactive decay of thorium-230. It becomes radium-226 as it tries to become stable. This process takes 75,000 years for 1/2 of the thorium in the sample to break apart into radium-226. 75,000 years for half of it to go away. So if you started with 100 grams of thorium-230, after 75,000 years, how many grams would be left, Allie? If you start with 100 grams of thorium-230, after 75,000 years, its half-life, how much would be left? What's half-life sound like? How much do you think is left when half-life occurs? 50. That's all it is. Okay, we try to make things kind of make sense. A half-life is the time it takes for 1/2 of the material to go away. So if it started out at 100, after a half-life, it'll be 50. After another half-life, Tona, how much will it have after its second half-life? If it was 50, another 75,000 years go by. Half of it will disappear if it decays. 25 grams. Because each time it disappears or decays half of it. So 100 decays into 50. 50 decays into 25. 25 will decay after another half-life into 12.5. It's half each time. 75,000 years for this one. All right, let's try another one. Radon 210. That's the isotope. It's going to undergo alpha decay. Go ahead and fill in the lines on the left-hand side of the reaction. The subscript, the superscript, and the symbol. Radon 210. We're going to start out with the symbol on this one. Put the information in there for the symbol on the left-hand side. Jaden, you're up. What's the symbol for radon? Perfect. Capital R, lowercase n, RN. Registered nurse in some fields. Not in this case. How many protons does radon have? Diesel. It has 86. So we put that on the subscript line. Sienna, you're up. What's the mass of this radon isotope? That's the average mass of all of the radons that exist in the world. We want to know just the one that we're dealing with in this example. What's the number that's the mass for this one specifically? You're looking at the wrong place. Either on your paper where you wrote it down or on the overhead where I have it as an example. (210). The name of it is its mass. That's how we name an isotope. 210. That's the mass of it. That's its name. Radon-210. Questions about that first part? All right. The second part now, you should have decayed it, taking away an alpha particle. If you do, what's the mass, Brianna? 208. What's the mass of an alpha particle, Evan? Should be 206. Because you have 4 units that disappear, that leave, so take away 4. Of those, there's only 2 that are protons, protein. How many protons are left in this one if 2 leave? 4. That's the 2 piece. Top is the big number, bottom is the small number. If it has 84 protons, who haven't I called on up there? Does anybody have neglected? Don't want to skip anybody. I think everybody's gone. Let's go to Sam. What's the element number 84? I just can hear you. Polonium. Named after Poland. Polonium. 206. This isotope, radon-210, takes 2.5 hours to decay. Its half-life is only 2.5 hours. The last one was 75,000 years. This one breaks apart every 2.4 hours, about 2.5 hours. So after 2.5 hours, half of it's gone. Another 2.5 hours, 3/4 of it's gone. Much quicker half-life. Let's try some beta decay. For beta decay, remember it's a high-speed electron that's created when a neutron changes to a proton. In this case, I put the picture up here just to give you an image instead of just the name. You can simply write iodine 131. That's this example. Iodine 131. It's abbreviated I. If it undergoes beta decay, an electron leaves the nucleus. So that's that 0, -1. What that means to us is when it undergoes beta decay, the mass of the parent is exactly the same as the mass of the daughter isotope. The mass does not change because it's 0 for the particle that leaves. What does change, though, is the number of protons. It increases by 1. Mass stays the same. Number of protons increase by 1. So instead of being 53 protons, iodine, it becomes 54 protons, xenon. Same mass, because the daughter isotope of a beta decay is exactly the same as the mass of the parent isotope, 131. It just has 1 more proton than the parent. Questions? All right, let's try an example. Thorium-234. This one's half-life is 24 days. I'm just giving you out there so you start to realize that they're just all over the place with how long it takes them to half decay, half of it to break apart. Thorium-234. Go ahead and set it up on the left-hand side with the subscript, the superscript, and the symbol. The number of protons on bottom, the mass on top. All right, remember the symbol from last time? It was TH. We keep the same symbol. It never changes. It's always the symbol for thorium. Number of protons never change. It's always 90 for thorium. never anything else. 90 is what makes it thorium. What's different here, though, is the mass. Remember, the mass number is the specific mass of this isotope. On the periodic table, it tells you an average of all of them. This is the mass of this one. Any questions before we do the first beta decay? Or the second one of this? All right, if a beta particle leaves, the mass does not change. So if it doesn't change, Allie, what should the mass be on this one? 234. Doesn't change. What does change is the number of protons. Evan, how many protons should this one have? Remember, in a beta decay, a neutron changes into a proton. So it gains one proton. 91. That's all it happens. We made a proton. We didn't. It did. One more proton than it had before. If it has one more proton than it had before, go to Janelle. What element will that be if it has one more proton? 91. Good. Protactinium is how you pronounce that big long word. That's why we abbreviate a lot of things. It's much easier. Capital P, lowercase a, Pennsylvania in some places. Protactinium. Questions about a beta decay? Mass stays the same. Number of protons increase by 1. And the whole reason this is happening is because the atom is trying to become nuclearly stable. It's not stable now. It wants to become stable, so it starts changing the nucleus. Last one. Carbon-14 has a half-life of 5,730 years. This is the one we use in order to tell the age of things that were once alive, if they were alive in like the last 30,000 years. It works really well for those type of ranges. Carbon-14, go ahead and set it up and create the daughter isotope. See if you can get the right answer. Anybody want to give us the information for the parent isotope? Evan, what's the parent isotope? Tell us the symbol first. It is. And second, what is the number of protons? So far, so good. And the mass of this isotope? You got it. That's what you should put down for the parent isotope, carbon-14. Question? I'm going to give it to one other person and see how Jaden does on this one. All right, Jaden, you're up. What's the daughter isotope? Give me the mass first. 14. It doesn't change. So I'm picking kind of the order that makes most sense to go in. What would be the number of protons for this one? 7. It gained 1, became 7. And now if it has 7 protons, what is its symbol? Nitrogen is an N. And that's what you would put. Questions about beta decay. All right, let's try a few examples now. Turning your workbook to page 24, I think it is. Page 24 has thorium-232 radioactive decay. We haven't done thorium-232 yet. We did 230 and 234. 232 is just a different isotope. There's all kinds of different isotopes of the elements. Some have as few as 2, others have as many as 60. It just depends on what element we're talking about, how many different mass units are in each isotope of that element. All right, go ahead and dive into it. See if you can get some decay series going. They go one after another after another. If you do it correctly, when you get to the very last one, the answer is lead 208. If you end up with lead 208 in the last line at the end of the series, that's the stable isotope. You did it correctly. Have at it. If you have questions, I'll come around and answer those for you. Once you've done a few, go ahead and check the overhead. Make sure you're doing them correctly. Numbers a little bit better, working with numbers. If you would, turn in your workbooks to page 26.